Hello, my name is Francis Pellets, and today I'll be presenting hydrophobic interactions to better understand implants. What is osteoarthritis? Osteoarthritis is one of the leading causes of pain and disability in adults of all ages, and it is the degradation of the cartilage within our large joints. Most commonly, it is the large load-bearing joints like the knee, the hip, and the spine. These tissues all have one thing in common, and that is their poor cellularity and vascularization, which means that they have a very limited blood supply, and because of this, they have a limited capacity to regenerate or heal, if possible at all. Commonly, there are not many therapies or surgical options to remedy this. For your therapies, you have debridement, which is the removal of damaged tissue, or you have microfracturing to promote blood flow to the region and hope that it will help restore some of the cartilage. And of course, common surgical interventions are what we all know. We have the total knee replacement and the total hip replacement. There are spinal surgeries, but they're less common and less desirable. And of course, with these replacements, there are reductions in mobility, and there is occasionally the degradation of the adjacent disc or tissue or wherever the surgical intervention was bound to. And of course, all of these treatments inevitably still lead to early onset osteoarthritis, so they're not ideal in the slightest. So what are scientists, doctors, and chemists all doing to remedy this problem? Since the 1950s, hydrogels have been thought as a biocompatible replacement for tissues. But it started off at a much more basic level with wound dressings and contacts. So what are hydrogels? In a sense, they are something that just holds a lot of water. When they were first made, they were very soft, they didn't have a lot of tensile strength, and they couldn't resist the shear forces that we now expect from hydrogels. What is the big change? They have started to cross-link polymer networks together so that they can still swell with water, and they still have the elastic and viscous components that we had come to expect from it. However, they have linked two different types of polymers inside of each other, one soft one and one hard one, and now it has more durability and it has a wider range of things that it can do, and scientists are starting to look at it not only for tissue engineering like I was discussing, but there's industrial applications and even drug delivery systems operate off of these hydrogels. There are a couple different types of newer hydrogels that have been developed within the last 4 years. Some of them are self-healing, tough, or even smart hydrogels. Of course, hybrid hydrogels between these types. But what are these? Self-healing is a bit more self-explanatory. If they sustain some sort of damage through physical stress, like someone stepping, or even oxidative stress, these hydrogels have a dynamic covalent and non-covalent bonds inside of them that are constantly working to return it to its original structure. Tough hydrogels are, like what I was talking about earlier, cross-linked polymer networks, which support load-bearing applications such as cartilage. And of course, there is smart hydrogels. And smart hydrogels are relatively new to this domain, and they essentially do something when something happens. What does that mean? Let's say that the pH goes up. They can have a hydrogel that will release a drug or medication when the pH changes or the temperature changes, or even small changes in electromagnetic fields, which might have more application with cardiac pacers or implants that have something to do with electricity. And of course, now in 2025, they have even pushed past this, which was 2024 and still fairly new, but they've started including hydrogels with growth factor beta, transforming growth factor beta, which promotes the differentiation of stem cells into chondrocytes, which promote and result in new cartilage formation. So they're doing very many wonderful things with hydrogels, but how does this have anything to do with chemistry? In the new applications of hydrogels as a cartilage replacement, they have started to use graphene-based 3D scaffolds to have a combination of biocompatibility, biodegradability, and even mechanical resistance. Now, this happens to cross over with a recent article in 2024 from Sun and the other authors, where they talk about hydrophobic interactions on a smooth interface. Now, what is a smooth interface? An interface is essentially anywhere where two states of matter interact. You can have a cup of water, and there's an interface between the glass forming the cup and the water inside of it, or even the air above the water and the water itself. It's just a boundary between two phases of matter. How do hydrophobic interactions actually work? Well, we're all aware of how the cage forms around a solute when in a bulk water solution. That is the hydration shell, where water molecules form hydrogen bonds around themselves and essentially encapsulate a solute. And while this is all happening, there is a whole bunch of free energy changes from the water and the interaction of the water with the interface with the interface, and the solutes, of course, with both the water and the interfaces as well. Now, there are a variety of bonds, such as double donor, double acceptor, which is our DDAA bond, and there's double donor, single acceptor, and single donor, single acceptor. What do these really mean? Essentially, if you're double bonded and double accepting, you are in your most stable form. So if you have a cup of water and it's all double bond, double accepted, you'll have a lower delta G, you'll have less free energy, and thus a more stable solution. Whereas if everything is a single donor, single acceptor, DA type structure, you have more free energy and it is a less stable solution. Sun's particular study examined the interactions of hydrophobic forces with a smooth interface by using molecular dynamic simulations operating on the NAMD package. This is just a type of software that allows both chemists and even people interested with how viruses interact with the human body to examine it, expedited of course, through the software. In this particular study, they had two different solutes. One was a methane molecule and another was a fullerene molecule. And if you're not familiar with carbon-60, it is essentially like a soccer ball of carbon atoms all linked together. And for this particular sim, they had those two molecules independently operating on a defined fixed path towards the smooth graphene interface. This was done within a fixed temperature, fixed volume box of about 4.4 nanometers by 4.4 nanometers by 4.2 nanometers, so an incredibly small box. While they were running the simulation, umbrella sampling was used to measure the free energy changes as the separation between molecules varied. These results were then analyzed using their weighted histogram analysis, and they calculated a potential mean force. What does any of this mean? This is essentially a numeric way to describe how favorable it is for solutes to approach or separate. And this allowed the authors to measure how graphene alters the hydrophobic forces within the water. And it is essential for this study as it reveals how the free energy landscape changed when the interface is introduced. Once the results were calculated, they had analyzed and determined that hydrophobic attraction exists in water and depends on both the solute size and the surrounding surface texture. Both methane and fullerene attract themselves in the bulk water solutions, yet attraction is significantly stronger for the fullerene molecule. Once the smooth graphene entered the bulk water solution, it weakened the solute-solute attraction, and it promoted the solutes to come attract to the graphene interface. As a result, solutes tended to migrate to the interface instead of remaining in the bulk water. When the surface of the hydrophobic solute comes into contact with smooth graphene, the amount of water at the interface actually decreases while bulk water increases. At the solute-water interface, where the solute and the water meet, water molecules form fewer hydrogen bonds, allowing the solutes to aggregate and bulk water to maximize its hydrogen bonding. And the final piece of the story comes from polymer science. There was a recent study that showed that at higher temperatures, above 248 Kelvin or about negative 13 Fahrenheit, the entropy of the system increases and hydrophobic polymers actually collapse into a globule state, and this helps to minimize the hydration free energy as the hydrogen bond network around them becomes less stable. And this is the same principle that we see in the simulation study, where near a smooth surface, hydrophobic molecules like methane and fullerene move towards the interface because it lets the surrounding water reorganize and lower the overall free energy. And whether it's a polymer folding or the solute migrating to the surface or the interface, the system is always trying to find the lowest energy configuration. And this principle seems to be exactly what current implant designers are using to control these hydrophobic regions in polymers and essentially control the water structure around it to improve lubrication and enhance the performance of the new theoretical implants. And when I first started looking into this, I thought that this was something that no one was doing, and I found older studies talking about polymers being a possible viability, but I was really surprised to see in the last year or two that this has become like a exploding field of topic. And then here are the references for this. And if you have any questions, please email me. Thank you.